Welcome back to this module on VLIW processes. In this and the next lesson, we will look at some challenges of VLIW processes and potential solutions to these challenges. In particular, in this lesson, I will discuss VLIW scheduling modules and how the VLIW code size can be reduced. This lesson is based on section 3.7 and Appendix H of Hennessy and Patterson, the main textbook for this course. It is also based on a book by Joseph Fisher, Paolo Faraboshi and Clifford Young called Embedded Computing, a VLIW approach to architecture, compilers and tools. And I would like to thank Paolo Faraboshi for sending me some of his slides. This lesson covers 4 challenges for VLIW architectures. What are these challenges? I will talk about the challenge of scheduling for non-unit assumed latency or NUL. I will talk about the large code size problem generated by VLIW compilers. I will talk about the complexity of the register file and the forwarding logic. And at the end, I will talk about control hazards and what I can do about them in VLIW. The normal execution model is UL. UL stands for Unit Assumed Latency. That means that the semantics of a program is that each instruction completes before the next one is issued. Although we do pipelining, it is not visible in the program execution model. Whatever architectural technique we apply, we always make sure that each instruction gets the most recent results. And this is the meaning of the conventional sequential model. When we go to VLIW, however, this model doesn't work anymore. We have to employ a model called non-unit assumed latency or NUL. That means that at least one of the operations has a non-unit latency L, and the program's semantics is such that before the operation completes, the next L-1 instructions have already been issued. In other words, it takes L cycles for the results to become visible. To make the NUL model a little bit clearer, here is an example. Let us assume we have again our conventional 5-stage pipeline. As before, the register file read takes place in the second half of the clock cycle and the register file write during the first half. But we made a mistake during the implementation. We forgot the forwarding hardware. On this pipeline, we execute the following code. We write 1, 2, 3, 4 sequentially to register 1 and then add register 1 to itself to obtain the result in register 2. Under the UL model, the result will be 8 because the last result in register 1 is 4. If we have NUL, however, the latency of an add is 3 clock cycles. Then the value read by the final add is the value written by the second instruction. So register 2 will be 4 at the end of this execution. So the pipeline is visible under the NUL scheduling model. To support NUL, 2 scheduling models are common. One is called the equals model and the other one is called the less than or equals model. Equals means that each operation takes exactly the specified latency. So the destination register will not be written until the specified latency has passed. Compilers can work with this model if the latency is fixed. But if the latency is difficult to predict, compilers have big difficulties generating efficient code. For example, how do we know whether a load will hit the cache or not? Compared to the other model, the less than or equals model, the equals model requires fewer registers to store temporary results. In other words, it reduces the pressure on the register file, or the register pressure. In addition, there are heavy requirements on the exception model. The less than or equals model, on the other hand, allows operations to take shorter than or equal to the specified latency. This means that the destination register can be written from the time of issue until the latency expires. It simplifies the implementation of precise exceptions, but puts heavy pressure on the register file, because a register may not be reused from the time the instruction is issued until its worst case latency. The less than or equals model also enables binary compatibility if in the next generation the latency has decreased. Now this brings us to the next challenge, the large code size. VLIW processors, it's in the name, have very long instructions. This indicates, what is usually the case, that the compiler cannot always find sufficient number of parallel operations to fill all the slots. Some slots need to be filled with no ops, which causes waste. Here's an example. We have 2 loads, but for the rest we cannot fill. Therefore, 3 knobs have to be inserted. What most VLIWs support are instruction formats of variable length, or the instructions are compressed in memory to avoid having such excessive code size. But knobs is not the only reason why VLIWs have large code size. It's also because the compiler has to use a lot of loop unrolling to find parallel operation. A second reason why the code size is large. How can a VLIW schedule be encoded compactly using horizontal and vertical knobs? This example shows a schedule for a 4-wide VLIW machine over 8 cycles. In figure A, blue boxes indicate knobs in the original schedule. Figure B shows the temporarily equivalent instruction stream made up of 0 to 4 operations per instruction with variable width instructions. The instruction length might be encoded using start bits, stop bits, or templates in each case. Darkened vertical bars show the end of each instruction. Figure C shows the corresponding memory image for this instruction stream. Cycles 6 and 7 are complete knob cycles, and thus are replaced by a vertical knob instruction, represented by the gray box in figure C between operations E0 and operation F0. Instruction boundaries are still portrayed in the memory image, although they are of course encoded within the constituent instructions and operations. This is an example of mask-based VLIW encoding. The idea behind mask-based encoding is to add mask bits or templates to a VLIW instruction to identify what goes where in the expanded instruction buffer. And at the same time to pre-compute the address of the next program counter, the next PC, so that we can keep filling the pipeline. In this example, the mask field contains both the dispersal information and the information to compute the next PC, expressed as number of operations. The figure shows a 2-deep instruction buffer FIFO, and the concept can easily be extended to other configurations. Then the question is, when do we decompress? There are basically 2 approaches for that. Either we decompress when fetching from the L1 instruction cache, or we decompress when doing the cache refill, meaning we fetch from the memory or the second level cache to the instruction cache. All the approaches have their advantages and disadvantages, as is the usual case in this field of computer architecture. When we decompress between the core and the level 1 cache, the advantage is that we use the cache space as effectively as possible. Only real operations are contained in the cache and no operations. The disadvantage, and that is really a big disadvantage, is that it might increase the length of a cache access. And this is a problem because the cache access is typically on the critical path. That means that if we make it only a little bit longer, it has an immediate effect on the cycle time of our processor. Another option is to decompress during cache refill, meaning between memory and the level 1 cache. The advantage is the opposite of the disadvantage of the first approach. We can decompress during the cache refill, so we have some time available for it, so it will not kill our cycle time. The disadvantage is the opposite of the advantage of the other approach, because now we have less effective use of space because our cache contains no ops, which is of course a pity. So what can also be done here is to combine the two approaches. That means we do a two-level decompression. That means on iCache refill we do a complex depression, for example some form of Huffman decoding, and on instruction fetch we do a simple decompression, for example using the mask bits that I presented earlier. This completes this lesson. Thanks for watching. In the next lesson I will discuss two other challenges of VLIW processes, namely the complexity of the register file and how to deal with control hazards. Hope to see you back.